Over the next hour, I will guide you on a fantastical journey through the vast and boundless ocean of stars. Please prepare yourself. Our exploration of the universe is about to begin. We often tend to perceive the cosmos as an infinitely deep, impenetrable darkness, pierced only occasionally by the faint and lonely light of distant stars. Yet, hidden within the vast reaches of space lie breathtaking wonders beyond human imagination. Crimson halos of glowing nebulae, the radiant blue brilliance of massive stars, and the intense ultraviolet emissions of quasars come together to weave a dazzling cosmic tapestry. Our journey begins near the Orion Nebula. From there, we will fly along the radiant spiral arms of the Milky Way, passing through dazzling star clusters and mysterious dust clouds. We'll then traverse the icy vacuum of interstellar space to reach the majestic Andromeda Galaxy. Along the way, we will cross the shadowy depths carved out by massive cosmic voids, enormous rifts in the fabric of space. Eventually, we will gaze upon the universe in its entirety, bearing witness to how the eternal laws of nature govern its chaos and disorder. Within the Milky Way are countless stellar nurseries. Some are relatively small, while others stretch tens or even hundreds of light years across. These massive nebulae, composed of interstellar gas and dust, are being relentlessly compressed by gravity. Against the backdrop of the cosmic abyss, most of these nebulae remain nearly invisible. However, some structures are visible to the naked eye from Earth. Among the most prominent is the Orion Nebula. Located 1,344 light-years away, the Orion Nebula lies in the middle of what is known as Orion's Sword, a line of 3 stars in a straight formation. Because of its enormous size and relatively close proximity, this nebula has fascinated astronomers since the earliest days of stargazing. Today, it is one of the most thoroughly studied celestial bodies. In 1993, the Hubble Space Telescope captured its first images of the Orion Nebula, revealing its rich spectrum of colors. Most of the material appeared in hues of red or bluish-violet, but spectral analysis uncovered something strange: unusually bright green light in some of the nebula's outer regions. This puzzled scientists for a long time, as the radiation did not match any known chemical elements. Some even speculated about the existence of a hypothetical stellar element, a substance unknown on Earth but possibly common in cosmic clouds. However, with the advancement of science, researchers eventually identified the source of the glow as extremely thin ionized oxygen. This discovery also helped explain the strange luminescence observed in many other nebulae, including our own sun's surroundings. To date, over 3,000 stars have been discovered within the Orion Nebula, along with vast clouds of interstellar gas and a large number of protostars. All these astonishing celestial bodies are packed within a region approximately 23 light-years in diameter, constantly engaged in complex and delicate interactions. The total mass of matter gathered in this region is equivalent to about 10,000 suns. When we observe the Orion Nebula up close, we can distinguish several prominent areas, among which the most striking is the Trapezium Cluster, an open star cluster around 300,000 years old, consisting of 8 main stars. Some of the stars in this region are part of binary systems, while others exist in isolation. Within the Trapezium Cluster, the brightest members are a group of 4 stars labeled using Latin letters. These stars are tightly concentrated within a region approximately 15 light-years in diameter, each possessing a mass between 15 and 40 times that of our Sun. Such immense masses suggest that these blazing stars are still very young. Among them, Theta Orionis C stands out as the most massive and luminous star in both the Trapezium Cluster and the entire nebula. This blue-white main sequence star has a mass of roughly 40 solar masses and a radius about 8 times that of the Sun. Its surface temperature reaches approximately 45,000 Kelvin, and its luminosity is an astonishing 250,000 times that of our Sun. The intense radiation from this star illuminates nearly the entire nebula. Yet curiously, there is a notable absence of interstellar gas in its immediate vicinity. This is because such stars typically generate powerful stellar winds that blow away the surrounding thin material. Just a few light years from the Trapezium Cluster lies another famous multiple star system, Theta Orionis. This system consists of 3 stars gravitationally bound together, situated near a glowing region of hot gas known as the Orion Bar. For a long time, this area remained hidden behind dense clouds of dust. It wasn't until the James Webb Space Telescope was launched that we finally received clear images of this region. The first star in the Theta-squared Orionis system has a mass slightly less than that of the most massive star in the Trapezium cluster and a surface temperature of around 35,000 Kelvin. The second star weighs in at approximately 15 solar masses and shines with 120,000 times the sun's brightness. The third star has a mass about 5 times that of the sun, with a surface temperature close to 14,000 Kelvin. But what truly fascinates astronomers isn't just the dazzling brightness of these stars. Deep within the surrounding clouds of gas and dust, the Webb telescope's infrared instruments have discovered never-before-seen objects, around 180 so-called protoplanetary disks. These are rotating, disk-like structures composed of gas and dust that encircle newly formed stars. One such disk, named Orion 294-606, measures a stunning 913 astronomical units in diameter. Thanks to its unique orientation, facing directly toward Earth, we are able to clearly observe its structure and scale. It is believed that, within a few million years, this system will evolve into a main sequence star, potentially giving rise to a planetary system with multiple exoplanets. The night sky seen from such future worlds would be nothing short of breathtaking, vividly glowing curtains of nebulae, with starlight far denser than what we observe from Earth, streaming through the heavens. Occasionally, massive vortices of luminous gas might swirl across the sky, covering half the horizon and turning the night into a semi-transparent twilight. If we zoom out to observe a wider region of the nebula, we find that much of its volume is filled with extremely thin gas. At its core lies a region dense with highly ionized hydrogen, constantly absorbing the high-energy radiation from nearby stars. This interaction heats the gas to around 10,000 Kelvin. However, at the outer edges of the nebula, the temperature drops rapidly. The resulting pressure differences and the collisions from stellar winds cause the material in the nebula to move at high speeds, sometimes forming enormous vortices traveling up to 50 kilometers per second and spanning areas larger than our solar system. In certain regions, astronomers have detected long, thread-like structures stretching across several light-years. These filaments are composed of relatively cold molecular hydrogen and do not contain methane, ethane, or water mixtures. Farther out, we approach the core region of the nebula. This core region is wrapped in a vast cloud of colder, denser gas. Here, the radiance of bright stars interweaves with the glow of ionized hydrogen, forming a magnificent and colorful curtain of light. Though hundreds of celestial objects remain hidden behind this veil in the visible light spectrum, modern infrared telescopes can penetrate the obscuring interstellar matter. By combining data from multiple observation sources, astronomers have discovered around 700 protostars in this region, each at different stages of evolution. Due to the relatively low gravitational compression of the surrounding interstellar gas, the density of these protostars is significantly less than that found in the nebula's core. This also indicates that most of these objects are very young, still in the process of forming into stars. According to modern theories of stellar evolution, the birth of a star typically begins with the gravitational collapse of an interstellar gas cloud. During this process, a massive nebula fragments into several tightly bound gravitational centers. These centers eventually give rise to protostars, leading scientists to vividly describe such regions as stellar nurseries. At a certain point, when the internal pressure of the collapsing gas balances out the gravitational force, a protostar reaches a temporary state of equilibrium. The remaining material forms a massive, swirling disk that is gradually drawn in by the forming star, while other parts are ejected far beyond the system's boundaries. The strengthening magnetic fields of young stars accelerate ionized particles along magnetic field lines, producing outflows that can reach speeds of several hundred kilometers per second. When these high-velocity particle streams collide with the surrounding gas clouds, they create massive vortices and hemispherical structures known as Herbig-Haro objects. During this interaction, some of the kinetic energy is converted into light and heat, giving these peculiar formations their unique colors. Moreover, the extreme motion generates shock waves that disturb the surrounding material, shock waves that can be captured by telescopes. Because these stellar nurseries often contain many closely spaced protostars, each emitting multiple outflows, Herbig-Haro objects exhibit a wide variety of shapes and colors. These features are unstable and ever-changing, typically dispersing entirely within tens of thousands of years. During that time, they can traverse distances ranging from 1 to 3 light-years. Currently, around 400 such objects have been identified within the Milky Way, though estimates suggest the total number may exceed 150,000. This astonishing natural phenomenon is considered a special variant of protostellar outflow. Some resemble bullets in mid-flight, hundreds of astronomical units in diameter, traveling at incredible speeds. These cosmic bullets have also been observed in the Orion Nebula. They race through the sparse hydrogen clouds with ease, generating shock waves that span vast distances. Spectral analysis reveals that the leading edges of these bullets contained iron atoms, which glow in the infrared spectrum. Estimated to be about 1,000 years old, the exact origin of these bullets remains a mystery. Some scientists speculate that they may have been launched during a cataclysmic event in the past. As we continue our exploration, we find that the Orion Nebula is actually part of a much larger cosmic structure known as the Orion Molecular Cloud Complex. This vast formation spans several hundred light-years and stretches across nearly the entire Orion constellation, visible from Earth's night sky. Within this complex lies the famous Horsehead Nebula, named for its resemblance to the silhouette of a horse's head, a dense cloud of dust roughly 3.5 light-years in diameter. Against a backdrop of crimson glow, the contours of the nebula appear even more sharply defined. Near the Orion Nebula lies another remarkable cosmic structure, known as Barnard's Loop. This is an emission nebula roughly 300 light-years in diameter, believed to have formed over 3 million years ago. It originated from the overlapping shock waves of several nearby supernovae, which compressed gas and jet streams into a vast arc-shaped cloud. Several young stars are now gathered within this sparse stellar cluster, emitting a gentle red glow that lights up the surrounding nebula. Despite the Orion Nebula's breathtaking beauty, it is, on a cosmic scale, a fragile and transient entity. The combined effects of stellar winds, radiation pressure from young stars, gas ejections, and turbulent vortices are continuously dispersing its material into surrounding space. At present, the nebula has already lost around 60% of its original mass. In roughly 100,000 years, its remaining material is expected to dissipate entirely. This brilliant, multicolored cloud will fade from existence, leaving behind a loose stellar cluster similar to the Pleiades. The young stars will initially travel together through space, but eventually, each will go its separate way, finding its own place within the vast expanse of the Milky Way. Long before the invention of telescopes, humans could already see a glowing band stretching across the sky, a captivating and mysterious phenomenon that inspired countless myths and legends. Yet it took thousands of years of scientific progress to uncover its true nature. The Milky Way is not a divine pathway, but rather the collective glow of hundreds of billions of stars so distant that their light blurs together into a diffuse sheen. The idea that stars might form part of a single grand structure was first proposed by Immanuel Kant in 1755. He also hypothesized that some of the nebulae discovered by astronomers could in fact be distant star systems, other galaxies. This visionary idea was far ahead of its time and was initially dismissed by many of Kant's contemporaries. It wasn't until the early 20th century, with advancements in observational technology, that scientists confirmed the existence of other galaxies. In 1936, Edwin Hubble introduced a classification system for galaxies, many of whose principles remain in use today. According to this system, the Milky Way is a barred spiral galaxy. Though it took billions of years to reach its current form, our galaxy is a true survivor in the cosmos. Some of its globular clusters contain stars that were born around 13 billion years ago, almost as old as the universe itself. At the same time, certain regions of the Milky Way are still active stellar nurseries, constantly giving rise to new stars. Data collected so far suggests that the Milky Way is relatively large by astronomical standards. Its galactic disk spans approximately 200,000 light-years across, and its halo extends even farther into space. The galaxy contains at least 200 billion stars of various types, along with 250 to 1,000 billion brown dwarfs. It also harbors over 1 trillion planets, countless smaller celestial bodies, and vast quantities of cosmic dust and interstellar gas clouds. Yet all of this conventional matter makes up only a small fraction of the Milky Way's total mass. Approximately 90% of the galaxy's mass consists of what is known as dark matter, a mysterious substance that emits little to no visible light and remains largely undetectable, yet dominates the gravitational landscape of our universe. Yet, despite its invisibility, dark matter plays an active and essential role in gravitational interactions. Even though most of a galaxy's mass cannot be seen directly, scientists can still calculate it. To do this, they study the motion of stars orbiting the center of the Milky Way. Based on current estimates, the total mass of our galaxy ranges from 800 billion to 1.5 trillion solar masses. The structure of the Milky Way is remarkably complex. Today, our journey takes us into its very center. Although this region is heavily obscured by thick clouds of gas and dust, we are fortunate to observe it through what is known as the radio window, an area of space with relatively low dust content that allows radio waves to pass through. Like most spiral galaxies, the center of the Milky Way harbors a supermassive black hole, surrounded by an accretion disk with a radius of approximately 3 light-years. This black hole is known as Sagittarius A, the closest object of its kind to Earth. It has a mass of about 4.3 million times that of the Sun, and its radius is no more than 16 million kilometers, 3 times smaller than the orbit of Mercury. The first detailed data on this galactic nucleus came from years of observation and intricate calculations. It wasn't until May 12, 2022, that the Event Horizon Telescope captured the first ever image of the Milky Way's central black hole, finally confirming long-standing hypotheses. Stars near the galactic center are densely packed. Over 6,000 stars have been detected within just 3 light-years of the black hole. Some of these stars have orbits that scientists have been able to trace with remarkable precision. For example, one blue-white star, designated S62, passes within just 17.8 astronomical units of the black hole, closer than Uranus is to the Sun. At that point, it reaches a velocity of 6.7% the speed of light. At such extreme speeds, classical Newtonian physics breaks down, and relativistic effects become significant. For instance, the orbit of a star like S62 precesses, its axis shifts by 75 arc-minutes with each complete revolution. This behavior is a striking confirmation of general relativity in action. As we journey further through this region, we encounter several massive star clusters with a combined mass of about 1 million solar masses. Around 200 light-years beyond this area, astronomers suspect the presence of another massive black hole, potentially weighing in at 100,000 solar masses. Moving onward, we reach the central molecular zone, a structured region stretching 1,600 to 1,900 light-years across, with a mass exceeding 60 million solar masses. This area is filled with stellar nurseries and molecular clouds, along with protostars and remnants of supernovae. The clouds here are primarily composed of dense molecular hydrogen, with temperatures ranging from 50 to 600 Kelvin, equivalent to -223 degrees to +327 degrees Celsius. Spectral analysis reveals that, in addition to hydrogen, these vast clouds also contain carbon monoxide, methanol, and phosphoric acid. As we pull back from the galactic center, we see it is surrounded by a bright, massive elliptical structure stretching 10,000 light-years in length and about 7,000 light-years wide. Its total mass is an incredible 10 billion solar masses. Due to the sheer density of starlight in this area, it's impossible to count the stars individually. This elongated elliptical region forms what is known as the bar, the foundation of the Milky Way's spiral arms. At the far end of this galactic bar, we encounter the Stephenson 2 star cluster, home to one of the largest known stars in the universe, Stephenson 218, a stellar giant with a radius 2,150 times that of the Sun. Unfortunately, the chances of finding exoplanets around this extraordinary star, Stephenson 218, are extremely slim. Even if planets once existed in its vicinity, this supergiant would have long since engulfed them during its dramatic expansion. While the galactic center contains billions of stars and undoubtedly hosts a vast number of exoplanets, the likelihood of discovering habitable worlds in this densely populated region is significantly lower compared to less crowded areas of the galaxy. The dense concentration of stars in the galactic core destabilizes planetary orbits, making it difficult for exoplanets to maintain long-term orbital stability. Moreover, the intense radiation emitted by these stars is lethal to any known form of life. That is why astronomers have defined a specific region within the Milky Way as the Galactic Habitable Zone, a giant ring-shaped area with a radius between 22,000 and 29,000 light-years from the galactic center. This zone contains stellar systems with the highest potential for hosting life. The inner edge of this habitable zone is too close to the galactic center, where radiation levels are too high. The outer edge, on the other hand, lacks the heavier elements essential for planet formation and life. However, mathematical models show that stars can migrate across thousands of light years, potentially moving into or out of the habitable zone over time. Therefore, even if an exoplanet lies within the zone, it doesn't automatically imply that its surface conditions are suitable for life. Continuing our journey outward from the galactic center, we reach one of the Milky Way's most spectacular components, the galactic disk. This disk consists of two distinct parts. The first is known as the thin disk, which has a thickness of about 1,000 to 1,300 light-years and a visible radius extending up to 50,000 light-years. The outer edges gradually fade into space, with the most distant stars lying as far as 100,000 light-years from the galactic core. Approximately 80% of the Milky Way's visible mass is concentrated in this region, which is also the last major structure to have formed in the galaxy's history. The second component is the thick disk, which shares a similar diameter with the thin disk, but is 4 times thicker and much more diffuse. It is composed primarily of very old stars and contains almost no interstellar gas. Observations of specific stars and simulations suggest that between 11 and 8 billion years ago, the Milky Way underwent a significant galactic merger. It absorbed another galaxy, an ancient structure now referred to as Gaia Enceladus. This event contributed billions of stars, vast amounts of interstellar gas, and a substantial quantity of dark matter to the Milky Way. The merger likely played a crucial role in forming the galaxy's thick disk and triggered a wave of new star formation fueled by the additional gas. Within this grand spiral structure, the Milky Way is generally recognized to have 2 major arms, the Scutum Centaurus arm and the Perseus arm, as well as 2 smaller arms, the Norma arm and the Sagittarius arm. Some models also include a 5th major spiral arm named after the Cygnus constellation. These spiral arms are regions of exceptionally high stellar density, and most of the galaxy's interstellar gas is concentrated here as well. As a result, the star formation rate in these arms is 3 to 5 times greater than the galactic average. Newly formed stars typically exist in loose star clusters for the first few million years. However, because these clusters lack the gravitational strength to hold the stars together long-term, they eventually disperse, causing the young stars to drift apart. Following the Sagittarius arm, we arrive at a branching point where it connects with the Perseus arm. This stellar structure, known as the Orion arm, is approximately 110,000 light-years long and about 3,500 light-years wide. At a distance of 27,000 light-years from the galactic center lies our very own solar system. From Earth's perspective, the center of the galaxy appears as a dark abyss, shadowed by dense clouds of cosmic dust. This dark abyss is known as the Great Rift, a vast expanse of space that obscures much of the Milky Way. It is filled with enormous clouds of interstellar gas and dust, with a total mass estimated to be over 1 million times that of the Sun. Though the Great Rift is nearly opaque in visible light, the material within it actively emits radio waves and thermal energy. Spectral analysis reveals that these clouds are primarily composed of hydrogen, along with trace amounts of more complex molecules, such as alcohols and amino acids. The Great Rift is considered a potential stellar nursery, yet it remains relatively inactive for now. It may be a long time before the first generation of stars ignites within its depths. Let us continue beyond the galactic disk. While the spiral arms, bright and clearly defined, draw most of our attention, the Milky Way extends far beyond them. A closer look reveals the galaxy's most expansive and diffuse component, the halo. This spherical structure extends outward up to 260,000 light-years from the galactic center, though it accounts for only a few percent of the Milky Way's total mass. The halo contains numerous globular clusters made up of exceptionally ancient stars, as well as several large stellar streams. One such stream, the Sagittarius stream, consists of thousands of stars that form an elongated ellipse nearly perpendicular to the galactic disk. Models suggest that these stars were likely captured by the Milky Way's gravity from a dwarf satellite galaxy known as Sagittarius D, which lies about 500,000 light-years from the galactic center and is expected to be completely absorbed in the coming billions of years. Another dwarf galaxy, located in the Canis Major constellation, has already met a similar fate. Nearly destroyed by the Milky Way's gravitational pull, it had millions of its stars stripped away, extending as far as 200,000 light-years into space and merging with other galactic populations. This stellar stream, with a total mass of roughly 100 million solar masses, has orbited the Milky Way 3 times. In addition to these faint stars and scattered clusters, the galactic halo also contains vast quantities of hot gas, with temperatures soaring to several million Kelvin. It is also believed to house large amounts of dark matter dispersed throughout the galactic surroundings. This forms what is known as the dark halo, which may extend up to 2 million light-years from the galaxy's center. It emits no detectable electromagnetic radiation and can only be observed through its gravitational effects. The dark halo remains one of the great mysteries of astrophysics, yet it plays a vital role in maintaining the structural stability of our galaxy. Around 2.5 million years ago, a giant star in the Andromeda galaxy neared the end of its life near the galaxy's core. It perished in a cataclysmic explosion, unleashing trillions of tons of searing plasma that formed a massive cloud, obliterating nearby planets and moons. Powerful electromagnetic pulses radiated outward across the universe, destined to travel for millions of years, one day reaching Earth. In 1885, astronomers around the world turned their attention to an astonishing celestial event, a sudden, intensely bright flash in the region of the Great Andromeda Nebula. For a brief time, the light from this outburst overshadowed the nearby stars. This spectacular supernova was designated Andromeda S. Its unusual characteristics puzzled astronomers for years. Yet just 6 months later, the star rapidly dimmed and soon vanished from the sky, forever. Sadly, at the time of this explosion, humanity's understanding of the universe was still limited. Astronomers lacked the tools to measure distances to celestial objects, and the true nature of galaxies, let alone the scale of the cosmos, remained largely unknown. For a long time, the bright point of light in Andromeda, also referred to as the M31 object, was believed to be a simple reflection nebula on the outskirts of the Milky Way. However, with the emergence of more powerful telescopes and the rapid advancement of space exploration technologies, our understanding gradually shifted. In the 1920s, the observations of Edwin Hubble and other astronomers provided conclusive evidence that the Andromeda Nebula was in fact a separate galaxy, one remarkably similar to our own Milky Way. A century has passed since that groundbreaking revelation, and science has made enormous strides since then. We now know that the Andromeda Galaxy has a spiral structure and contains roughly 1 trillion stars. Its diameter exceeds 150,000 light-years, and its total mass is estimated to be between 800 billion and 1.2 trillion solar masses, comparable to that of the Milky Way. This relatively moderate mass is thought to result from a high proportion of red dwarf stars and a lower concentration of dark matter. Like all spiral galaxies, Andromeda features a massive central core composed of millions of densely packed stars. The brightness of this core is so intense that observational instruments cannot distinguish individual stars, making it impossible to directly track the remnants of the supernova observed in 1885. Records from that time only confirm that the event occurred near the galaxy's center. It wasn't until 1988, 103 years after the event, that astronomers discovered a small nebula not far from Andromeda's core. Against the dazzling backdrop of the galactic center, this dark spot stood out. Spectral analysis and motion modeling eventually confirmed that this was the remnant of the Andromeda S supernova, making it the first supernova ever detected beyond the Milky Way. A closer examination of Andromeda's core reveals some truly unusual features, setting it apart from typical spiral galaxies. Uniquely, it possesses a double nucleus, an enigmatic structure whose origin remains unresolved. The larger of the two components is slightly offset from the galactic center and consists of a massive cluster of bright stars, spanning roughly 5 light-years in diameter. The other component, much dimmer and more compact, lies closer to the true center and measures about 1.3 light-years across. It is believed that this central region conceals a supermassive black hole weighing approximately 50 million times the mass of the Sun. The true nature of this peculiar dual-core phenomenon remains a subject of scientific debate. One hypothesis suggests that, in the distant past, Andromeda absorbed a significant satellite galaxy, dispersing its core, which now appears as the brighter region near the center. Another theory posits that the galactic core is in fact a single structure, visually divided by a thick, opaque band of cosmic dust. A century has passed since that groundbreaking revelation, and science has made enormous strides since then. We now know that the Andromeda galaxy has a spiral structure and contains roughly 1 trillion stars. Its diameter exceeds 150,000 light-years, and its total mass is estimated to be between 800 billion and 1.2 trillion solar masses, comparable to that of the Milky Way. This relatively moderate mass is thought to result from a high proportion of red dwarf stars and a lower concentration of dark matter. Like all spiral galaxies, Andromeda features a massive central core composed of millions of densely packed stars. The brightness of this core is so intense that observational instruments cannot distinguish individual stars, making it impossible to directly track the remnants of the supernova observed in 1885. Records from that time only confirm that the event occurred near the galaxy's center. It wasn't until 1988, 103 years after the event, that astronomers discovered a small nebula not far from Andromeda's core. Against the dazzling backdrop of the galactic center, this dark spot stood out. Spectral analysis and motion modeling eventually confirmed that this was the remnant of the Andromeda S supernova, making it the first supernova ever detected beyond the Milky Way. A closer examination of Andromeda's core reveals some truly unusual features, setting it apart from typical spiral galaxies. Uniquely, it possesses a double nucleus, an enigmatic structure whose origin remains unresolved. The larger of the two components is slightly offset from the galactic center and consists of a massive cluster of bright stars, spanning roughly 5 light-years in diameter. The other component, much dimmer and more compact, lies closer to the true center and measures about 1.3 light-years across. It is believed that this central region conceals a supermassive black hole weighing approximately 50 million times the mass of the Sun. The true nature of this peculiar dual-core phenomenon remains a subject of scientific debate. One hypothesis suggests that, in the distant past, Andromeda absorbed a significant satellite galaxy, dispersing its core, which now appears as the brighter region near the center. Another theory posits that the galactic core is in fact a single structure, visually divided by a thick, opaque band of cosmic dust. Unfortunately, due to the great distance and the galaxy's inconvenient angle in space, astronomers have yet to gather sufficient data to confirm either hypothesis. Meanwhile, as we continue traversing the central region of the Andromeda galaxy, we come across one of its most mysterious celestial objects. Though it bears a rather unassuming name, its defining characteristic is extraordinary. It is nearly invisible in even the most powerful optical telescopes. Yet it becomes the brightest point in the entire galaxy when observed in the X-ray spectrum. Observations reveal that this mysterious object is a binary system composed of two components. One is a low-mass neutron star with a radius of only a few dozen kilometers, rotating fully around its axis approximately once every 3 seconds. The second object in the system is a larger, though relatively dim, celestial body, most likely a red giant. Calculations show that the total mass of both components does not exceed 3 solar masses. They are in extremely close proximity. Every 4 hours, the neutron star is eclipsed by its companion, causing a sharp drop in brightness, which then returns to its original level. Because of this close distance, the neutron star is very likely gradually siphoning material from its companion star, increasing its mass over time. This mass transfer is expected to continue for tens of millions of years. Eventually, tidal forces will tear the second star apart, transforming it into a bright, scorching ring-shaped nebula. Interestingly, this remarkable object is just one of countless stars that densely populate the central core of the Andromeda Galaxy. Together, they form a massive nuclear bulge approximately 12,000 light-years in diameter, distinctly elongated in shape. Andromeda M31 also has a prominent bar-shaped structure, though it is aligned edge-on from our perspective on Earth, making it nearly invisible to ground-based observers. Estimates suggest the bar measures around 17,000 light-years in length and approximately 62,000 light-years in width. About 30% of the galaxy's total mass is concentrated within this central region. As we move further out, we observe that the ends of this bar serve as the bases for 2 enormous spiral arms. These majestic arms wind outward from the galactic center, separated by dark gaps significantly wider than those in our own Milky Way, measuring up to 13,000 light-years across. According to astronomical models, Andromeda's spiral arms contain roughly 56% of the galaxy's stellar mass, along with a substantial portion of its dark matter. Under the influence of gravity, interstellar gas and dust concentrate within the spiral arms, giving rise to numerous stellar nurseries, the very regions where new stars are born. Over time, these gas and dust clouds evolve into open clusters and stellar associations filled with young stars. The light from these stars is reflected and scattered by cosmic nebulae, endowing Andromeda's disk with a mesmerizing array of shimmering colors. Among these stellar clusters resides one of the galaxy's most extraordinary stars, Andromeda AE. It is one of the brightest stars in the entire galaxy, a scorching blue giant. Its brightness varies irregularly, without any predictable pattern. Stars of this type are known as luminous blue variables, LBVs, and they are exceedingly rare, with only a few dozen known in the universe. Due to their extremely high temperature and internal pressure, stars like AE Andromedae exist in a state of constant instability. Their internal evolution is largely chaotic and unpredictable. Occasionally, streams of hot plasma within the star collide, generating intensely bright flares that can increase its brightness by several orders of magnitude. The most powerful of these flares are thought to boost the star's luminosity by millions of times, producing some of the most brilliant outbursts in the observable universe. This phenomenon can easily be mistaken for a supernova explosion, and indeed, such an eruption could occur at any moment. Given the star's inherent instability and its immense distance from Earth, measuring its parameters is an extremely challenging task. However, with the aid of modern ultra-precise telescopes, astronomers have determined that this blue giant has a mass between 50 and 120 times that of the Sun. At the peak of its pulsation cycles, AE Andromeda's radius expands to approximately 55 times that of the Sun, just slightly smaller than Mercury's orbit. Its surface temperature approaches 20,000 Kelvin, and its luminosity ranges from 500,000 to 700,000 times that of the Sun. Like all blue giants, AE Andromedae generates an extraordinarily strong stellar wind. Calculations estimate that this wind can reach speeds of up to 100 kilometers per second, causing the star to lose roughly 20 trillion tons of material every second. This equates to an annual mass loss equivalent to 10 Earth-like planets. Yet for a star of such immense size, the effect is negligible. It will complete its entire evolutionary cycle long before losing even 1/10 of its total mass. Now estimated to be about 2 million years old, AE Andromedae is already well into its life cycle, although by cosmic standards that lifespan is but a fleeting moment. According to current projections, the star will go supernova within the next 1 million years, leaving behind a black hole shrouded in a vast cloud of gas and dust. When discussing stellar ages, it's important to note that stars are not evenly distributed throughout a galaxy. This uneven distribution allows us to peer into Andromeda's past and gain insights into its formation. The oldest stars, those aged between 11 and 13 billion years, are concentrated in the galaxy's central bulge. In contrast, the disk and spiral arms mainly host younger stars, most of which formed 3 to 4 billion years ago. Many stars in the galaxy's star-forming regions are only a few million years old. This indicates that, in its early evolutionary stages, the Andromeda galaxy was significantly smaller than it is today, and likely had a more elliptical shape. By analyzing individual stars within Andromeda, astronomers have also proposed an important but conditional concept: the galactic habitable zone. It is believed that the central region of the galaxy, due to its high stellar density, intense radiation, and unstable planetary orbits, is not suitable for the origin of life. On the other hand, the galaxy's outer regions are too metal-poor to support the formation of many Earth-like planets. Therefore, only the middle region of the galaxy, at a distance of tens of thousands of light-years from the center, is considered theoretically suitable for life. It is within this region that a faint celestial object called Mega ML7 resides. This is a red giant with relatively low mass, about 50% that of the Sun. In 1999, astronomers were fortunate to observe a rare gravitational microlensing event involving this distant, unremarkable star. This chance occurrence allowed them to study the object in far greater detail. Measurements revealed its mass, spectral characteristics, and a surface temperature of approximately 3,700 Kelvin. But the most important discovery was related to the star's trajectory. It exhibited rhythmic deviations from the main direction of motion, oscillations interpreted as a strong indication of the presence of a massive companion body, possibly a binary partner. This hypothetical object has been named Mega ML7b and is currently considered a potential exoplanet. If its existence is confirmed, it would become the first exoplanet ever discovered beyond the Milky Way, a historic milestone in astronomy. Although information about this object remains limited, calculations suggest it is most likely a gas giant with a mass approximately 6.3 times that of Jupiter. Additional reports indicate that the chemical diversity within this system may be comparable to that of the solar system. This suggests that a wide range of planetary types could exist in its vicinity. Not only gas giants, but also rocky, Earth-like planets. Another striking feature of the Andromeda galaxy is its abundance of star clusters and stellar associations, far exceeding the numbers found in the Milky Way. According to current data, Andromeda hosts around 460 known globular clusters, roughly 10,000 open clusters, and several dozen large stellar associations. Some of these are concentrated near the galaxy's center, others are dispersed throughout the halo, and many are aligned along the spiral arms. Among the largest and most prominent of these structures is NGC 206, a stellar association located near the edge of Andromeda's disk. Once classified as a globular cluster, its immense size led to its reclassification as a stellar association. Within this 200 light-year wide region lie approximately 300 extremely luminous stars and countless fainter ones, totaling around 200,000 solar masses. Its combined brightness is so great that it can be observed from Earth using standard telescopes. Observations suggest that NGC 206 formed from the merger of at least two massive gas and dust clouds, divided by a prominent band of interstellar dust. One of these clouds is approximately 10 million years old. The other is around 50 million years old. The resulting supercloud became a gravitational hub for interstellar gas, eventually developing into an expansive star-forming region. Over time, some of these stars will disperse into the surrounding space, while others may evolve into a new globular cluster. The Andromeda galaxy's disk contains many such structures, not all of which are native. It is believed that many of these massive associations are remnants of ancient cosmic cataclysms. Based on astrophysical models, Andromeda has already absorbed more than 100 satellite galaxies over its lifetime. Some were nearly obliterated, while others transformed into enormous stellar streams. One of the most violent of these events may have been the collision with the M32 galaxy. This dense elliptical galaxy lies just 177,000 light-years from Andromeda and spans about 8,000 light-years in diameter. Despite its modest size, M32 holds an astonishing mass of over 1 billion solar masses. At its core lies a supermassive black hole weighing in at 2.5 million solar masses, an unusually massive object for such a compact galaxy. In fact, M32 is likely the remnant of a much larger galaxy that survived a catastrophic encounter. According to data from the Spitzer Space Telescope, approximately 800 million years ago, a massive satellite galaxy plowed through the disk of the Andromeda galaxy, leaving a vast hole in one of its spiral arms. This collision stripped M32 of most of its stars, rendering it unable to regain its original form. It may once have been a fully formed elliptical galaxy, or perhaps even a small spiral galaxy, before being torn apart in the aftermath of that cosmic collision. Today, only the core remains. Aside from M32, the Andromeda galaxy is accompanied by approximately 30 satellite galaxies, all bound to it by invisible gravitational forces. The largest of these is M110, a galaxy roughly 15,000 light-years in diameter. The rest are mostly dwarf spheroidal galaxies located within a range of 1 million light-years. Together, they form the Andromeda subgroup, which itself belongs to the larger local group of galaxies. Other members of the local group include the Milky Way and its satellite systems, as well as the Triangulum Galaxy and various other celestial bodies. Drawn together by the inescapable force of gravity, the galaxies in this group are moving toward a common center at a speed of about 300 kilometers per second. On the cosmic scale, our Earth is nothing more than a tiny fragment of rocky debris, racing through the infinite void at incredible speed. It has orbited the Sun for billions of years, maintaining a distance of approximately 150 million kilometers. Yet the true scale of the solar system extends far beyond what we typically imagine. Modern theories define the boundary of our solar system as the outer edge of the Oort cloud, which stretches to around 100,000 astronomical units from the Sun. Beyond this lies the vastness of interstellar space, an environment so sparse that on average, there is only 1 hydrogen atom per cubic centimeter. In the Milky Way, the average distance between stars is measured in light-years. A photon of light departing from the Sun can travel all the way to Proxima Centauri without encountering a single particle of matter. This immense, silent emptiness forms the most basic and fundamental fabric of the universe. It spans the Milky Way, separating all celestial bodies, stars, planets, black holes, white dwarfs, ultra-dense neutron stars, and diffuse nebulae. Zooming out beyond our galaxy, we find that the Milky Way itself is surrounded by even deeper voids. For instance, between us and the Andromeda galaxy lies a vast, intergalactic desert measuring 2.5 million light-years across, a space large enough to fit 25 Milky Ways end to end. Yet even this is only a tiny fragment of the universe's great abyss. The Milky Way, Andromeda, the Triangulum Galaxy, and their 100-plus satellites are all gravitationally bound together, forming a structure known as the local group, which spans approximately 10 million light-years in diameter. This local group is part of an even larger cosmic structure known as the local sheet, a flattened arrangement of galaxies spanning 46 million light-years across and about 5 million light-years thick. The local sheet, in turn, belongs to the Laniakea supercluster, one of the largest known structures in the observable universe. Astonishingly, at the very edge of the local sheet, the nature of space changes dramatically. Here lies an immense dark void, a vast cosmic abyss known as the local void. In fact, the local sheet forms one of the walls that define the boundary of this colossal emptiness. The edge of this void connects to the Perseus-Pisces supercluster and the Pavo-Indus supercluster. This void is divided into regions by several thin filaments of galaxies and intersected by wide channels that connect it to nearby voids such as the Bootes void and the Hercules void, creating a single, integrated network of cosmic emptiness. Due to the expansion of the universe and the gravitational influence of surrounding matter, the volume of the local void is slowly increasing. Its current estimated diameter is about 150 million light-years, with the distance to its center being at least 70 million light-years from Earth. Meanwhile, approximately 3.2 million light-years away, the local void occupies a significant portion of Earth's night sky, covering about 40% of it. The Milky Way's galactic plane, rich with bright stars and massive nebulae, blocks our view of the central region of the void, but its edges remain observable. In 1854, a dwarf spiral galaxy was discovered just north of the Hercules constellation. It was later named NGC 6503. With advancements in observational technology, astronomers determined that this galaxy lies near the center of the local void. It is renowned for its stunningly colorful appearance. Its spiral arms are dotted with bright red clumps of glowing hydrogen and bluish nebulae, all indicative of active star-forming regions. Its center, obscured by cool gas and dusty clouds, presents a majestic brown hue. NGC 6503 spans approximately 30,000 light-years in diameter and is located about 17 million light-years from Earth. Due to the gravitational pull of the Virgo supercluster, this galaxy is moving toward us at a speed of about 43 kilometers per second. Estimates suggest that as it continues its approach toward the local sheet, it may eventually fill its surrounding space with interstellar hydrogen, triggering a new wave of star formation. In the coming billions of years, the number of young stars in this region could potentially double, revitalizing the galaxy with fresh stellar energy. The movement of NGC 6503 offers a compelling glimpse into how cosmic voids may have formed. It is believed that the foundation of the large-scale structure of the universe was established within the first few minutes after the Big Bang. During this early phase, an era of chaotic interaction between matter and energy, immense cosmic upheavals rocked the newborn universe, producing regions of local density and emptiness. Dense clumps of matter eventually gave rise to protogalactic clouds, while regions of lower density evolved into the vast voids. Over time, the persistent influence of gravity magnified these contrasts, pulling stars and cosmic gases into dense clusters and leaving the surrounding space increasingly sparse. Observations indicate that most galaxies formed between 10 and 13 billion years ago. Furthermore, there is no significant age difference between galaxies located in voids and those embedded in the filamentary structures of the cosmic web. This supports modern theories about the formation of the universe's large-scale structure. According to other hypotheses, the void might contain vast amounts of the universe's most mysterious substance, dark matter. This invisible mass exerts gravitational force, yet its true nature remains beyond current scientific understanding. Even more audacious theories suggest that at the core of cosmic voids might lie clumps of antimatter, or even more exotic, replicated forms of matter not yet known to science. Though intriguing, these ideas extend well beyond the boundaries of mainstream scientific consensus, making them difficult to confirm through observation or experimentation. To date, only 2 isolated galaxies have been identified within this massive void. One of them, UGC 2627, is a spiral galaxy similar to our Milky Way. The second, UGC 2629, is a small elliptical dwarf galaxy. Both are located near the center of the void, approximately 185 million light-years away, and separated from one another by only a few 100,000 light-years. It's possible that more lonely galaxies lie hidden within the darkness, but the plane of the Milky Way obstructs our view. Meanwhile, the Virgo supercluster, alongside 4 other massive superclusters, forms a colossal filament of galaxies known as the Laniakea supercluster. This grand structure contains more than 100,000 galaxies and spans over 500 million light-years. Its gravitational center is a mysterious anomaly known as the Great Attractor, located about 250 million light-years from Earth. Remarkably, Laniakea itself is just one component of an even larger flow of galaxies. When we look farther out, we find this region surrounded by an unprecedented cosmic abyss. The light from distant galaxies is swallowed by its emptiness, and even elusive neutrinos, particles that rarely interact with matter, may take billions of years to traverse this void. It's astonishing to think that despite continuous advancements in astronomical observation, this enormous void was only discovered a little over a decade ago. In 2013, a team of astronomers at the University of Wisconsin-Madison, led by Professor Amy Barger, set out to measure the distances between galaxies. During this process, an unexpected and astonishing fact was uncovered. The Laniakea supercluster and much of the surrounding superclusters are enveloped by a previously unknown cosmic void. Calculations revealed that the diameter of this void exceeds that of any previously known structure of its kind. The sheer scale of this newly discovered void was so immense that it called into question several foundational principles of cosmology. It became clear that the universe is far more complex than we had imagined. This groundbreaking research is now considered one of the greatest astronomical discoveries in recent years. The scientists' work revealed that our galaxy and its neighboring systems reside near the center of what may be the largest known supervoid in the observable universe. This enormous structure was named the KBC void, after the initials of its three discoverers. Observations suggest that the KBC void is roughly spherical in shape, with a diameter possibly exceeding 2 billion light-years. Based on current models, the Milky Way lies hundreds of millions of light-years from its assumed center, with a similar distance to the edge. The discovery of the KBC void has helped resolve a long-standing puzzle in cosmology. As we know, the universe is expanding, and all galaxies are gradually moving away from each other. The speed of this motion, when measured, gives us the Hubble constant, a key physical constant describing the rate of universal expansion. However, discrepancies arose depending on where and how this constant was measured. Calculations based on nearby galaxies suggested that the rest of the universe was expanding too slowly. In contrast, measurements using distant galaxies indicated that the local universe, including our Milky Way, was moving faster than expected. The discovery of the KBC void provided a solution. Galaxies within the void, such as the Milky Way and its neighbors, are influenced by the stronger gravitational pull of structures outside the void. This added gravitational force subtly stretches our galactic neighborhood in multiple directions, altering local motion and skewing observational data. Even more surprisingly, the KBC void is so vast that it not only contains superclusters but also encompasses other voids. Both the local void and the torus void are considered parts of its grand structure. However, despite its immense size, the KBC void is not entirely empty. It contains sparse galaxies and cosmic material. Yet when placed against the backdrop of the entire observable universe, which spans approximately 93 billion light-years in diameter, the KBC void still appears as just a faint dark spot. When we view panoramic maps of the cosmos, we find many such dark patches similar in size to the KBC void. Most of them fit well within the framework of modern physical theory, but a few exhibit traits that are surprising and difficult to explain scientifically. One of the most notable among these is the Boat's supervoid, also known as the CMB cold spot. It is estimated to be between 500 million and 1 billion light-years in diameter, and it lies 6 to 10 billion light-years away from the Milky Way. This makes it one of the largest single structures in the universe's large-scale architecture. Located in the southern hemisphere of the Earth's sky, the Boat's void spans a region several times larger than the full moon. Yet it is completely invisible to the naked eye. It can only be observed using specialized telescopes that detect cosmic microwave background, CMB radiation, subtle remnants of the early universe. Thanks to these powerful telescopes, astronomers discovered that within the cold spot, the residual cosmic microwave background, CMB, radiation is approximately 70 microkelvin colder than the cosmic average. This deviation is nearly 4 times stronger than the most extreme anomaly previously recorded, and its immense size makes it one of the most mysterious cosmic features, demanding further study. Currently, scientists believe that as CMB radiation travels across hundreds of millions of light-years, its energy is subtly influenced by the gravitational pull of distant superclusters. This interaction saps the lingering heat from the Big Bang, rendering the cold spot cooler than its surroundings in microwave images. However, this effect alone cannot fully explain the observed cooling. calculations indicate that the gravitational influence of external galaxies accounts for only about 25% of the anomaly. It is hypothesized that the remaining 75% might be due to the influence of dark matter, or even more intriguingly, concentrated dark energy deep within the void. Yet solving this cosmic puzzle will take time. The butterfly effect. This leads us to a concept first articulated by meteorologist Edward Norton Lorenz, known as the butterfly effect. Lorenz proposed that even a tiny change in initial conditions could, through a chain reaction, result in unpredictable and major consequences. This idea is now a foundational principle in the scientific field known as chaos theory. To better understand the connection between the flapping of a butterfly's wings and a destructive weather event, let's go back to 1961. At the time, Lorenz, a mathematician and meteorologist, was experimenting with early computer models to simulate atmospheric flow and predict weather patterns. He believed that with computational power, weather could be forecasted with unprecedented precision. To speed up the process, Lorenz broke the simulation into segments, using the final values of one phase as the initial inputs for the next. To save time, the computer rounded some values ever so slightly. These changes were minute, and according to conventional logic, should not have altered the final result significantly. But to Lorenz's shock, the outcomes of the segmented computations diverged dramatically from the continuous model. Subsequent investigations revealed that the equations Lorenz was using were not perfectly suited for atmospheric modeling. However, as is often the case in science, an apparent error paved the way for a remarkable discovery. In seeking answers, Lorenz realized that the system's possible solutions clustered around two main regions, which he termed attractors. If each solution were plotted as a point in three-dimensional space, the overall pattern resembled the shape of butterfly wings. What was astonishing was this: a minuscule shift in starting parameters could cause the final result to leap from one wing to the other. The implications were profound. Interestingly, Lorenz was not the first to touch on this effect. German philosopher Johann Gottlieb Fichte and French mathematician Henri Poincaré had hinted at similar ideas in their writings. Nonetheless, it was Lorenz who turned a frustrating computational glitch into a powerful and elegant theory, one that would eventually influence disciplines ranging from meteorology to quantum mechanics, from climate science to economics. In doing so, he showed that even the tiniest tremors in a complex system can ripple outward, generating consequences far beyond their origin. In the decades that followed, hundreds of scientists contributed to the development of the concept of chaos, and the theory itself underwent significant evolution. Its mechanisms have since been used to describe a wide range of complex phenomena and processes, including turbulence, the evolution of biological species, social interactions, and fluctuations in stock markets. The laws of chaos help define everything from the motion of celestial bodies and stellar explosions to the rise of empires and the shifting of continents. To fully understand these factors and patterns, one must first define chaos from a scientific perspective. The first thing to note is that any chaotic structure still follows clear and rigorous physical laws. However, such structures are so complex that their behavior appears unpredictable. This is why they are referred to as systems of deterministic chaos. Their behavior is determined in advance, even if we can't forecast it precisely. This is what sets them apart from systems based on truly random events. In a chaotic system, if we observe its behavior repeatedly under identical initial conditions, it will always respond the same way. In contrast, a truly random system will yield different results each time. For example, experiments have shown that the decay of unstable atomic nuclei in radioactive materials is entirely governed by chance. While we can estimate how many atoms are likely to decay within a given time frame, current computational capabilities cannot predict the exact moment when a particular nucleus will decay. Mathematically, a system is considered chaotic if it exhibits nonlinearity, remains broadly stable yet contains at least one oscillating equilibrium point, and has a fractal dimension of no less than 1.5. Unless one is a trained mathematician, these criteria can be difficult to grasp. But in simpler terms, they can be broken down into three key characteristics. First, the system must be nonlinear. Imagine we influence a structure in some way and expect a predictable response. In a linear system, repeating this interaction multiple times would result in a total effect equal to the sum of each individual influence. But in a nonlinear system, the outcome may be greater or smaller than expected. This is exactly the kind of behavior Edward Lorenz observed in his weather simulations, an insight that pushed him to delve deeper into chaos. Second, a chaotic system must be sensitive to its initial conditions. This is known as the butterfly effect. It means that even the smallest change, seemingly negligible, can cause the entire system to evolve in a completely different way. Third, as the system develops, its various components should overlap and interact with one another. These interactions are often ignored in classical physics, but overlooking them can lead to major gaps in understanding. It is precisely this tracking of multi-level interactions that makes models of chaos theory so detailed and so closely aligned with real-world phenomena. Let us now go back 13.8 billion years to the moment of the Big Bang. In just a few quantum moments after that primordial event, there was no matter or energy as we know it today. The four fundamental forces were still unified under a strange, singular force. At that time, the physical laws we currently understand did not yet apply, but other, equally strict laws were already at work. These early rules predetermined how the system, the universe, would evolve in the future. In the nascent universe, even the tiniest change at any given point could completely alter the course of its future. Regardless of the cause behind such minute fluctuations, it's fair to say that our reality was born out of scientific chaos. Now imagine the universe approximately 1 million years later. Space had already begun to resemble the cosmos we recognize today. Although there were still no stars or planets, countless primordial gas clouds drifted across the young universe. Hydrogen was being compressed by gravity, forming gravitational centers that would become the very first stars. These gas clumps were distributed in an irregular and unsystematic fashion, and their masses were sufficient to exert mutual gravitational influence. If even one protostar were moved slightly or its mass altered, that change would not only affect its own evolution, but also that of nearby celestial bodies. This means that the laws of chaos continued to govern the cosmos. Over the billions of years that followed, the first-generation stars burned out and exploded, seeding the universe with heavy elements. New stars were born from hydrogen clouds, while nearby cosmic dust began to swirl into massive rotating disks, circular formations in which we can clearly observe familiar, chaotic motions and interaction patterns. Roughly 4.6 billion years ago, the solar system was formed in such a way. Our eyes can perceive only a fraction of the universe's astonishingly vibrant nature, and some dimensions of reality can only be revealed beyond the visible light spectrum. It is only through advanced observation techniques that we are able to reach out and witness this breathtaking beauty. At every moment, hundreds of telescopes are scanning the universe, which means we are continuously advancing toward new knowledge and groundbreaking discoveries.